Alright, hello everybody, this is Fahad Salahat. I am going to make a tutorial video on how to use the ML-CCD, which is the machine learning concrete cover delamination software. Let's get started and do the following. First of all, I usually like to create a hosting folder. So in this case, I called it ML-CCD on the desktop. It's an empty folder, as you can see here. So the second thing, you go ahead and open the project location on the GitHub and pull the project documents. You can do that in multiple ways. Some people usually prefer to do that using copying the URL of the repository. Others prefer to do that using Visual Studio. You can do that. The same results you will have eventually. Actually, let's just copy the URL and go ahead and on your local machine open Visual Studio and clone repository, and here is the URL that we copied. For the path, I would like to go ahead and have the ML-CCD that we created for that purpose, which is the empty folder. And as you can see, I am going to open the empty folder now, and on the side I am going to have the Visual Studio. So once I get this order clone, you will see that the ML-CCD has just filled everything. Now we will talk about the requirements on your local machine on how to make this software run without any problems. As you can see here, because I created the code and developed it on my machine that I am recording this video on, I mostly have all my requirements satisfied and available. However, I deleted this package intentionally just for the sake of showing you how the download of your requirements and the packages that you need to run this code, how the process goes. So in the code folder that we created, which is the ML-CCD, you will see a text file called requirements, and if you open this text, you will see that all the requirements needed for that you will have to download in order to make this code work properly. Now, because I have all of them downloaded, but actually I deleted from my site packages. What I mean by deleted from my site packages is where your packages live, and this is simply, if you go to Python environment, this is the environments that we are talking about. Now this is the local environment that I have on my machine. We're gonna change that in just a second, but for now I'm gonna hit the right click and open this in a folder. And if you go to the lib folder here, you will see all the packages that anybody or anyone has a local environment will usually, whenever you download a package on your local environment, you will find your local packages in this site packages folder, which is, let's look for site, yeah, here. So here is all the packages that I downloaded on my local machine, and that's why you can see most of them are not underlined, because they are available in this spot. However, pandas table, I just deleted it from here, and if I am to so you can see here there is pandas, which is different from pandas table. pandas table is this guy here, but this is the distribution information. It doesn't have the pandas code, so I deleted the file that has the code itself. Like here you can see that you have pandas and pandas distribution information and the libraries. These are three different things. I deleted the pandas code so that we can go ahead and download it, how you are going to download the rest of the packages you need. So let's go ahead and tell that the requirements. I am gonna need only pandas table, so thank you. I'm not gonna download excuse me, I'm not gonna download the rest of these, and I will save the text file, and we will go back here and pay attention to the message that Python or the Visual Studio tells you. It's basically saying that we detected a requirements text, which is the packages that you will need to make this code run. Would you like to create a virtual environment and download that? I highly recommend this approach so that you do not download all the packages on your local site packages path. And let's go ahead and click create virtual environment. This is the project where you will have, or the folder that you will have the virtual environment located in. This is the name of the virtual environment, and the base interpreter is Python 3.11. This is the minimum. The minimum actually is 3.10 to run this code, and we will pull the requirements from this, which is the text file that we talked about, and I am going to go ahead and create this virtual environment. Now it says here that virtual environment is being created. I'm gonna give permission. And it says that it is installing pandas table. So and now it has been successfully installed. What just happened is that now, well, just to let you know that tkinter is integrated library within Python. It doesn't have to be installed on any machine. Whenever you install Python, this comes with Python. So what happened actually is that I installed the pandas table, but then I did not install those. But why they are underlined? Because now my environment has changed to Python environment, in the virtual environment that I created. So simply to you will not have to deal with all of this whenever you clone this on your whenever you clone this on your machine. You will have the requirements, all of them listed in your in this text file, and then you will have to download all of them, and then all of them are gonna be green, not underlined in green. So what I'm gonna do here is just to fix the problem that I made by deleting that package, and I am going to go to the virtual environment and see the site packages and have pandas table, this guy here. So I'm gonna copy this one and go to my site packages and paste it here, refresh this view and see pandas table. It's here. Now if I switch back to, if I select other environment, which is this guy here, add, and I remove the virtual environment that I created, this issue should be fixed. And here we go. All of these are now on my local machine. You will have all of these in good shape once you install the requirements folder, or I'm sorry, the requirements file that has all of them listed in this txt file, and they will be installed in an environmental in a virtual environment in your uh, in your local folder. So now let's proceed and run this software. It's now working properly. The first thing you will see here is the introductory interface on who developed this, which is myself, Salahat, and my co-developers, Professor Haider Rashid of Kansas State University, and Dr. Hudayfa Ashqar of Arab American University of Palestine. Now hit start and import the database. Now all of this is going to be in the same folder that was cloned from GitHub, and this is the database that we are gonna have installed. Now this is, let me just have this in here to be clear, and so this is the interface that reads the database, which is all the things you need to, or all the things that have been imported from the file. It says that the total number of beams is 70, which is the size of the current database that we have. Please feel free to enlarge and expand this database by installing or by doing the following. If you open the database, you can simply add more rows here to the database below this one, and it has to be with this arrangement. So pay attention to the units, don't change the units, because the software only now for now the software for now has the SI units and is not compatible with the American or the US system units. If you want to add, all the units are Newton for force, millimeter for dimensions or distances, a millimeter squared for area, and then you have megapascal for stress. So these are the things you have to pay attention for when you come to expanding this database. If you have more data points that you feel, they will improve the prediction model. The second one is called the new beam, and we will get to the point where you have the option. When you come to the prediction, you will have to fill the important parameters required for predicting the concrete cover delamination of any beam. If you can see, these are the values you will have to input on the software, so that for this purpose and for more convenience for the user, we give him the option, or her the option, to input more in a more flexible and user-friendly way, to give the user the option to input all the parameters in this sheet, and the software is going to pull and is going to read the sheet number 2 for parameters inserted here. Again, you will have to pay attention to the units, and everything has to be pulled from here. Now, for this point, the current version of the software reads just line 2 of this sheet. So if you have multiple beams that you need to test, it's just gonna go and read number 2. So I recommend that if you have multiple beams, just copy them somewhere here or in sheet number 3, and only input the parameters that you want to test, or for the beam that you are interested in row number 2. So this is the database Excel file that we pulled, and let's go back and talk about our software. After we imported the database, go ahead and do visit the unstrengthened capacity. This is a function that calculates the unstrengthened capacity for all the beams in the database, and the reason for this function is we are going to use the unstrengthened capacity in obtaining the strengthening ratio, which is the strengthened capacity divided by the unstrengthening or unstrengthened capacity. So we already have this function for you available, so it's just gonna calculate all the unstrengthened capacity. Well, what I mean by unstrengthened is the capacity of the beam with no FRB strengthening, so it's just conventional RC beam, and this function does that for us. Again, we have to proceed with the failure analysis, and this function actually is very important because it does the following. If you click obtain failure profiles, it's gonna come and obtain all the strain profiles for each one of the beams in the database, and based on the strain profile, all the stresses are calculated. And in this function, actually this is where the filtration of the bad beams, what I mean by bad beams, they do not satisfy or comply mechanics of RC beams and the fundamental theories, which are when you have the stress and the strain profile, you will have to calculate the equilibrium of the forces and moments around your neutral axis. So we do find the neutral axis by optimization, and once we find that, we will have to have the M verify, which is the moment verification, and the F verify, which is the force verification. So the M verify, and you can see that these M verify and F verify should be the same as the experimental. So if there is a flag, that means that either the beam failed in concrete crushing, which means that the strain is exceeding the limit strain of the strain that we had for the model, which is 0.003, which is some codes go to consider this as 0.0035, but in our code we consider the concrete crushing strain of 0.003. So this is a beam that is going to be excluded. And also other stuff you will kind of find here, which is convergence. What is that supposed to mean is you can see that the experimental moment and the verified moment do not match, and there is a difference between them. That means the beam is not in very well input data, so there is like some sort of errors in reporting the beam information from the source we pulled that beam and the information from. So all the other beams satisfied the equilibrium and passed this function, which is the failure analysis, which we consider it to be quality control over the data points that we have. So the other one, which is the trilinear function. If you perform the trilinear analysis, this is basically giving you a 3-point curve, which is a cracking point, yielding point. The cracking point is represented by the moment at the cracking level, the strain in the concrete at the cracking level, the neutral axis at the cracking level, the rotation of the section at the cracking level. You will find this information for the yielding as well and for the ultimate, and based on that you will decide what is the cracking or what's the failure mode of each one of the beams existed in the database. And in this one, for instance, you can see here FRP rupture, concrete crashing, and if you see here M experimental is larger than MN, this beam is going also to be excluded from the database, and the reason being is that we will use the trilinear representation on our code to drop the moment that we find the predicted capacity that we find. So if we are talking about a beam that has an experimental capacity that is larger than the ultimate capacity of the beam, this is also another sign that the beam was not reported, or the properties of the beam were not reported properly, or that our concrete crushing strain is not actually is low compared to the strain that happened in the experimental. But since all of the data points were good in shape and little beams did not actually conform, we will just consider this to be an acceptable concrete crushing strain, which is the 0.003. And that again, the trilinear, what we are going to use, or what we are going to use the trilinear relationship to drop a moment on the curve and obtain the rotation phi at that corresponds to that moment, and also we will obtain this strain in the concrete at the moment that we will project. ML, the machine learning training, is this the core of this project and this code. Our model now only adopts the random forest model, which we have here. The default values are encouraged to remain the same. However, if you have in mind different values, you are welcome to try them. And then we train the model based on the database we have. This is a very good actually option that is utilized and facilitated for the user. The user can input the percentage of the error that they are considering to be acceptable. If they consider 5% to be acceptable, they can show this error bar and see that most of the data points are within this range, almost within this range. So this is the one prediction over actual, that the green line is the matching, that like 100% accuracy. You can see here this is actually very far away from the actual, like the prediction is very far away from the actual, but most of the data points you can see that almost within 5%. If you flex the percentage of error to be about, let's say, 10%, now you can see that this covers almost every point, like every point in the prediction falls within range. Of course, you go up to 15 and more, you will have this model that is approximately predicting your failure very well. So if you feel you are by the way, the error percentage is just a visualization thing. It doesn't have to do with any prediction results. We will go to calibrate. We will have to calibrate the model later on based on the coming window. But this is just to show you that this is the accuracy of the model that you have for now. However, you might be interested to change these parameters, and now these parameters will affect your prediction accuracy. So if we go back to 5%, and let's try this to be 5,000, the number of trees. It's gonna take more time to train the model, but let's see if this is something doable or not. Okay, so now it has been trained based on 5,000 number of trees, and now we can show. I am not sure if this is much of if this makes any difference, so because I still can see this is far away and the rest of them. Maybe this has better prediction. I'm not sure if this improved or not, but if you are happy with what we had for the 500, and let's proceed with this. So after I click the run prediction button here, I will see the training parameters. These are just for your information. These are the parameters that were used in predicting the or in training the machine learning model. Here is the more important tab, which is the calibration. So it tells you that the relationship between the strengthening ratio, which is the M strengthened over the unstrengthened, is this, and based on the prediction results from that, this is the FF, where rho F actually is from the input, which is the area of FRB to the area of the beam. FF is the failure stress of the FRB, and this is the where we are actually this is the output of the machine learning prediction, which is the FF, and the rest of these are actually inputted from characteristics of each beam, which are rho S, the area of steel, Fy, D. So the strengthening ratio is coming from dividing the moment capacity obtained from the machine learning prediction and divided by the unstrengthened capacity that we calculated previously based on our function. So I can see that this point is noisy point. It does not actually reflect the actual behavior of the curve. So in order to calibrate, I can change the slope and the intercept of the red line here. In order to do that, I can now it's easy process. You can decide, it's iterative but it's easy. You can see that the slope of the green, I'm sorry, the slope of the blue dots are actually the slope is actually more than or larger than the red one. So I am going to increase the slope to, let's say, 0.75 and update correlation. I can see still the slope of the red line needs to be higher. I can go to 0.8, a little bit higher, let's say 0.82, a little bit higher. The slope, I'm now just working on the slope. Let's go on 0.83, sort of maybe 0.84. Okay, so I am happy with the slope now. So I can see that the slope is almost parallel to the blue dots. Now what I need to do is to lower my intercept. So I need to go and change this to, let's see, 1.2, a little bit down, 1.1, a little bit down, 1.05 maybe, 1.06. Okay. Well, I now have a very good and very perfect fit, and here is my relationship of the red line, which is going to be used in calculating my prediction. So y is the strengthening ratio and x is this ratio. So what I am going to use here when I fill the parameters required for the beam, it's simply gonna use this relationship and obtain the failure moment for us. So let's go ahead and see what are the options you have here. Fill from sheet 2 is what we discussed and seen in the Excel file here when we said that beam, a new beam is the sheet where you want to fill. If you do want to fill the form in the code here, so if I fill from sheet 2, you will find that everything here is coming from this row. And then if you decide that you want to change anything, you just change it from here and update the input. It's gonna take it from here as well and run results. Here is my results. So for the results, you will find that this is the unstrengthened capacity, this is the ultimate capacity, and the ultimate capacity is based on the failure mode that we found on the trilinear analysis. So this is the maximum capacity the mature maximum capacity that this beam can achieve, which is either concrete crushing or FRP rupture. This is the FRP strain, which is at the this is the FRP strain at the nominal, which is corresponding to the 20. By the way, the units here, if you see this number is very large, this is Newton millimeter. So if you divide by 10 to the power 6, it's gonna be 72 point something, which is kilonewton meter. So just pay attention that this is just a Newton millimeter. So the FRP nominal strain is the strain corresponding to the ultimate capacity of the moment. The FRP strain depending or D is the depending strain that happens for the premature depending failure mode, which is provided by the codes, design codes, and you can refer to that and find how to find it. And here the FRP concrete cover delamination, and you can see that the concrete cover delamination controls the three strains, and this is going to be the critical strain, which is the FRP cover delamination. Based on our prediction of the critical strain, which is the FRP concrete cover delamination, we found the x-axis. The x-axis is here, this x-axis. So if you found the strain, multiply it by the modulus of elasticity for your beam or your FRP, which is coming from here, it's going to find the x-axis, and then using this equation here, it's gonna give you the strengthening ratio. The strengthening ratio gives you here is the strengthening ratio, and finally it gives you the critical moment or the critical strengthening moment. So this is actually the output of our software. So again, and in summary, what you need to do is to train the model, enter the tab to calibrate this curve, and import your results here. Run the prediction based on the random forest. The prediction that were run will give you the effective or the critical failure strain. You come with the strain to this curve, and this curve gives you the strengthening ratio, and after the strengthening ratio is found, the multiplying the strengthening ratio by the capacity or the moment, you will find the unstrengthened capacity. You will find that you have the strengthened capacity based on concrete cover delamination failure mode. Thank you very much for watching. I hope you will find this software useful. Please let me know. You will find my contact information. Please let me know if you have any questions or suggestions that I can help you with. Again, thank you very much, and I'll see you in future developments or other softwares that we might provide you.